I'll just remind you, there are different conventions for B. This will be true if the units of B are reciprocal centimeters. Sometimes we write the energy of rotation as I'll write it this way. I used a tilde here. Now the units of this B tilde will be hertz. Or this text uses the notation where B has units of joules itself. So in this case, let's see. Yeah, so whatever, and now the units would have to be joules. So just to make this connection between what the book says and what you may have seen in quantum mechanics, this B has different conventions. Anyway, so that's the energy level, and the degeneracy as a function of J turns out to be 2J plus 1. So then, what we need to think about if we want to form Q is this. Right, so that's the rotational partition function in terms of this thing the book uses. So what do we do? Now, last time for vibration, there happened to be a convenient summation formula, convergence series, and so forth. I don't know of a convenient summation formula for this. So we'll talk about two different possibilities. Rotational levels are much more closely spaced than vibrational levels. So it turns out that at most temperatures you're going to use, probably, I mean, maybe not for you, because you deal with really cold stuff, and you know.
But you can integrate it.
Huh?
But you can integrate it.
You can integrate it as long as it's not too cold. If you're really cold, you can't do that. So if you integrate, this becomes, let's see, what's the simple thing to do? You have y equals j times j plus 1. And dy is equal to 2j plus 1 dj, so it's just anyway, so the final result is is this, where we now are defining a rotational temperature. So once again, the rotational temperature, just as the vibrational temperature, is not really a temperature, it's just a constant. Depends on the moment of inertia, Boltzmann's constant, and Planck's constant, that's all it is. So for any particular substance, it's a constant. It's not a temperature. So you have to ask yourself, when is this integration valid? Well, this integration would be valid as long as the rotational temperature is much less than the actual temperature you're talking about. And again, if you look on your text on a different page, on page 95. If you look at page 95, again they give a bunch of substances. Oh, now they've got bromine, by the way. And the vibrational temperature is 463, so it's above room temperature. But the rotational temperatures are on the order of one Kelvin or less, or 1 degree Celsius or less. 1 Kelvin or less. Only hydrogen and deuterium might give you problems. Hydrogen's is 85 K and deuterium's is 43 K. So if you're talking really cold, or liquid helium temperatures or something, you have to worry about that. Actually summing this series. Of course, if you got a computer, you can sum the series, who cares? Who cares? Way back in the day, you worried about this.
But if you are also at full temperature, and you were worried about integrating, you can just take a couple of the sums, right?
Exactly. Yeah. Actually, the text goes through a song and dance about how can we make this more accurate, and they talk about a particular way of summing that is clever, called the Euler-Maclaurin summation method. So if you want to be more accurate, you can use the result of the Euler-Maclaurin summation method, which I'm not going to go through. You can study on your own. It turns out that it's this. So you can keep as many terms as you want. The leading term, of course, is equivalent to our simple results. And then you have terms in theta r over t to some power, 1, 2, 3. So if you don't want to think very hard, you don't want to do this clever Euler-Maclaurin summation, you can just sum up this way. But for comparable accuracy, you'll need more terms here than you will there. So that's that. Before computers, of course, it was important to be clever like this. Now that we have computers, it really doesn't matter much. Be as accurate as you want. So what about the energy? Let's see, I think you can see that if you just use the first term, that's what you're going to get. And yeah. And if you want to be more accurate, you just keep more terms. And the heat capacity is this this familiar form of Nk. Remember that generally you have for rotation 1/2 kT for each rotational degree of freedom. For this guy, the rigid rotor, you can tumble like this or you can tumble like that. Those are independent. So that gives you the 2 times 1/2. The third would be rotation about the axis, but that's not proper. 0 moment of inertia and so forth. So that doesn't really quite make sense at the microscopic level to think about rotation about that axis. So that's why we just have 2 halves or 1 here. We'll see for polyatomics, of course, we'll have 3 halves or, yeah. So that's the rotation part. What else do I want to say? If you look at the population of a particular level, that will be equal to right? So you probably studied this in elementary quantum mechanics. You can see that if you think of the population as a function of J, it's a product of an increasing function of J and a decreasing function of J, normalized by Q. So it goes through a maximum, starts out at a small number and goes through a maximum. So generally, it works something like this. And the maximum is usually at just a couple of but it depends on the spacing. So you tend to have significant rotational excitation at room temperature in, say, a sample of gas, but not significant vibration on rotation. I'm just developing a physical sense for these things. So then to summarize for rotation, the rotational levels are, of course, degenerate. There's not an easy summation for this series in closed form. So we can make the approximation that the rotational levels are closely spaced, and it's good for most substances at most temperatures we care about. And when we do, we get this very simple form for Q rotation. We define the rotational temperature. And of course, the integral approximation is valid when the rotational temperature is very small compared to the actual temperature. We saw that we can be more accurate by keeping more terms in the series or creating a convergent series, with this clever summation formula. So you can make reference to this if you want to. And not surprisingly, the rotational energy was nkt, and the rotational contribution to the constant volume heat capacity was nk, what we've seen before. And we saw that the populations of rotational levels at usual temperatures are significant up through several values of J up to 3, 4, 5, and beyond. That's the bulk of this. Any questions? we have a little time and we could go on, but as I said, I don't want to go through the chapter too quickly. So I think I'll tell you what we'll take up next time. And if you have any questions on anything, bring it up next time, because I don't really want to start the classical stuff. I mean, we don't have a lot yet to do in this chapter. But what does remain is to treat everything we've said so far applies as stated to diatomic molecules as long as they're heteroatomic. But if they're homoatomic? What am I trying to say? Homoatomic? I'm all of a sudden I can't talk. If the two atoms are the same, then we have to take a little bit more into account due to some symmetry considerations. And that takes a little careful thought, actually. You have to think quite carefully. And then you'll see that it doesn't affect the vibrational part, but it affects the rotational part. And we'll see if the rotational and the nuclear part talk to each other. So that's what we're going to talk about next time. So that would be homonuclear diatomics. So I'm trying to say. All right?
Yeah.
All right, cool.